Hello students, so continuing our lectures on mathematical physics, we will first start with some basic concepts of vector calculus. First of all, the angle between two vectors. If A and B are two vectors, then the angle between them if is theta, then we can have cos theta is equal to A dot B divided by mod of A into mod of B. It basically comes from the fact that A dot B is actually AB cos theta. So there we can actually find out the value of this theta. And if the vectors are coplanar, that means they are on the same plane. That means if this is a plane, if there is a vector A and B, then A cross B is equal to 0, because A cross B is actually equal to a vector C which is perpendicular to A and B. So there are no vectors, so in that case it is equal to 0. And we introduce the concept of del here. This value means del by del x I divided by of j and del by del z of k, that means differentiation in x, y and z directions. And next there is something called a gradient. Based upon that del we can have gradient, we can have divergence, and we can have curl. So gradient is del phi, where this is a scalar quantity. Phi is a scalar, so it means that del phi by del x into I plus del phi by del y into j plus del phi by del z into k. It is basically the flux of like if it is a tap, the water coming out from this tap is denoted by this del phi, flux of vector. And the next is divergence. Divergence is like dot product. So del dot v, where this v is actually, this is a vector. So and it is and v is expressed as say v1i plus v2j plus v3k. So the divergence will be equal to simply del v1 by del x1 plus del v2 by del x2 plus del v3 by del x3. So even if del and v, those are vectors, so the dot product is actually a scalar. And here from scalar we are converting into a vector. So these two complement each other. And the next is the curl. Curl is also a vector. It's called, say, del cross, say, A. It is denoted by I, j and k, del by del x, del by del y and del by del z. And if A has got three components, A1, A2 and A3 in the I, j and k directions, it will be A1, A2 and A3. So this is also a curl of a vector. Now, very important function based upon this del is a del square. It's called Laplacian, and it is simply del square by del x square plus del square by del y square plus del square by del z square if you consider Cartesian coordinate system. However, in other coordinate system, it has got different forms, like in spherical coordinates. By spherical coordinates, I mean this is the case. Then there is a vector r. This is r. This is theta, and this is phi. So it's basically r, theta, and phi coordinate system. Here, del square is represented as 1 by r square del by del r square del by del r plus 1 by r square sine theta del by del theta of sine theta del by del theta plus 1 by r square sine square theta r square sine square theta del square by del phi square. This is how we present this Laplacian operator in spherical polar coordinates, and in cylindrical coordinates it is something like this, denoted by r and theta, and this quantity is z here. So I missed one thing in spherical polar coordinates. This is actually rho phi. So it is represented by r, theta, and z. So here del square is equal to del square by del r square for the radial part plus 1 by r d by dy. This is the radial part plus 1 by r square del square by del theta square plus del square by del z square. This is how to represent Laplacian in cylindrical coordinates. But from that, in vector calculus, we have two very important theorems based upon these divergence and curl. First one is called Stokes Theorem. It is represented in this fashion: A dot dr is equal to del cross A ds dot n ds. So it is a line integral, circular line integral, and it is a surface integral. So in words, you can write that the line integral of the tangential component of a vector. So let's write the Stokes theorem once again. A dot dr is equal to del cross A dot n ds. So you can write the line integral of the tangential component of a vector A of the tangential component of vector A taken around a simple closed curve, taken around a simple closed curve, which is C here, is equal to the surface integral of the normal component of the curve is equal to the surface integral of the normal component of the curl of the vector. So it is the Stokes theorem. Then we have divergence theorem. And it is expressed mathematically as volumetrical divergence of vector A dot dv is equal to surface integral of the normal component of the vector. So the volume integral is reduced to the surface integral. So these are some of the basic vector basics of some of the vectors. So we will directly switch on to something else. We will start with the gamma and beta functions. So a gamma function is written in this fashion: gamma n is equal to 0 to infinity e to the power minus x to the power n minus 1 dx, where the value of n is real and is greater than 0. And one of the identities of gamma function is gamma n plus 1 n is equal to n gamma n. So gamma n plus 1 is equal to n gamma n. If this continues, it will lead to n factorial. Then gamma 1 by 2 is equal to root pi, and so gamma 3 by 2 is equal to gamma 1 plus 1 by 2, and it is equal to half into gamma 1 by 2, and it's 1 by 2 into root pi, so it's equal to root pi by 2. Similarly, we can write gamma 5 by 2 as equal to gamma 1 plus 3 by 2, so that is equal to 3 by 2 into gamma 3 by 2, that makes it root 3 by 4 root pi. So using the same notion, we can generalize the concept. We can write that gamma n plus 1 by 2 is equal to 1 plus 3 plus 5, all odd numbers, till 2n minus 1 into root pi by 2 to the power n, where n takes the value 1, 2, 3, dot. Or based upon this relation, we can also write gamma minus n plus 1 by 2. If we change the sign of the value, then n, then it will be simply equal to minus 1 to the power n into 2 to the power n root pi divided by 135 till 2n minus 1. So what has happened? This entire portion comes down, this one goes up, and in addition there is minus 1 to the power n. And this formula that we previously discussed, that is gamma n plus 1, gamma n plus 1 is equal to n factorial, and it is also equal to closely equal to 2 pi n to the power n e to the power minus n, and this is known as Stirling's formula. N tends to infinity, and this is known as Stirling's formula. So this is about gamma function. Similarly, beta function can be defined gamma function had only one parameter, and beta function has two parameters, m and n. So it is represented by b m n, and it is in fact related to gamma function also. So b m n is equal to gamma m into gamma n divided by gamma m plus n, and bmn is equal to bnn. So it's symmetric in terms of its parameters, and we can write the expression of the bmn as bmn is equal to 2 into integration 0 to pi by 2 sine 2m minus 1 theta into cos 2n minus 1 theta d theta. And the other way of presenting the beta function as 0 to infinity t to the power m minus 1 divided by 1 plus t to the power m plus n into dt. So these are the beta and gamma functions. Apart from these two functions, we will also discuss some special functions and properties, and in fact these are based upon some differential equations like Hermite. So Hermite polynomial, or whatever you can call it as h and x, so it is actually a solution of a differential equation which is called Hermite differential equation, and it is given as double differentiation y double dash minus 2x y dash plus 2ny is equal to 0, where n is 0, 1, 2, 3 dot dot dot. And so Hermite polynomial, this is the Hermite polynomial, and the n is actually the degree n. So a solution of this differential equation in terms of Hermite polynomial is expressed as h n x, which is equal to minus 1 to the power n e to the power x square into d square dn by dxn e to the power minus x square, and this expression is popularly known as Rodrick's formula. And there are a few basic relationships basic properties of Hermite. So like we have h0x is equal to 1 and h1x is equal to 2x. This is Hermite polynomial, comes in the harmonic oscillator problem in quantum mechanics. So later on we'll see the use of this Hermite polynomial. So h1x is equal to 2x, h2x is equal to 4x square minus 2. H3x is equal to 8x cube minus 12x, and h4x is equal to 16x to the power 4 minus 48 x cube x squared plus 12. There is a generating function of Hermite polynomial. It is e to the power 2tx minus t square, and it is equal to n is equal to 0 to infinity h n x t to the power n divided by n factorial. And there are some recurrence relation. Hermite polynomial, like h dash nx is equal to 2n h n minus 1x, and h n plus 1x is equal to 2x h to the h nx minus 2n h n minus 1x. Apart from that, we have some orthonormal properties. Of Hermite polynomial, like minus infinity to infinity e to the power minus x square h mx h nx dx is equal to 0 if m is not equal to n, and another one is minus infinity to infinity e to the power minus x square h nx whole square dx is equal to 2n into n factorial into root pi. So these are the two orthonormal properties of Hermite polynomial. Now, similar to Hermite, we have another polynomial based upon a differential equation. It's called Lazda in French. So the differential equation is 1 minus x square double differentiation of y minus 2x y dash plus n into n plus 1 y is equal to 0, where n takes the value 0, 1, 2, 3, and by solution of this we get the Lazda polynomial lnx, not lnx, pnx. Pnx, and Pnx is equal to 1 by 2n n factorial dn by dxn x square minus 1 to the power n. The first few polynomials of Lambda are p0x is equal to 1 and p1x is equal to x, p2x is equal to 1 by 2 3x square minus 1, and p3x is equal to 1 by 2 5 x cube minus 3x, and lastly p4x is equal to 1 by 8 35 x to the power 4 minus 30x square plus 3. Similar to Hermite, it has also got a generating function. And it is 1 by root 1 minus 2tx plus t square, and it is equal to summation n is equal to 0 to infinity pnx t to the power n. And there is some recurrence relation. Relation is x into p n x, p n dash x is minus p dash n minus 1 x is equal to n p n x. This is the first recurrence relation. The second recurrence relation is p dash n plus 1x minus p dash n minus 1x is equal to 2n plus 1 pnx. While coming to the orthonormal properties of Lambda, these are minus 1 to 1 pmx pnx dx is equal to 0 for m not equal to n, and minus 1 to 1 pmx whole square dx is equal to 2 divided by 2 plus n plus 1. And there are a few more properties of Lambda, like pn1 is equal to 1 and pn minus 1 is equal to minus 1 to the power n, and pn minus x is equal to minus 1 to the power n into pnx. So there are a few more properties of Lambda, and based upon Lambda we have another function. It's called associated Lambda function. And the differential equation is 1 minus x square y double differentiation minus 2xy. It is similar to what we have in the Lambda. Only difference is that this last term where we have L into L plus 1 minus, this comes in spherical harmonics, very useful equation, spherical harmonics, 1 minus x square into y is equal to 0, and there are two parameters here. You can see in the last it was only n or m. Here we have m and l as well, so that is why PLMX, this is the polynomial or the function, whatever you may call it, is 1 minus x square to the power m by 2 into dm by dxm PLX. This is the expression of the associated Lambda function, where this PLX is the Lambda function discussed previously, and L is a positive integer. So relationship between PLOX, where m is equal to 0, is equal to PLX. That means for m is equal to 0, the associated Lambda function, it gets converted into only the normal Lambda function, and this is the condition: m has to be equal to 0. And the second thing is that PLMX is equal to 0 if m is greater than n. The orthonormal properties of Lambda function. Orthonormal properties are minus 1 to 1, P m n x. Actually, this one should be L, not m. Pmnx into PLMX dx is equal to 0 if n is not equal to L. If these two are not equal, then this is equal to 0, and minus 1 to 1 PLMX whole square dx, this is equal to 2 into L plus m to the power factorial divided by 2L plus 1 into 1 minus m, sorry, L minus m factorial. So let's write it in a different form. Is equal to 2 by 2L plus 1 divided by L plus m factorial divided by L minus m factorial. So this is all about associated Lambda polynomials or functions. The next type of function that we will discuss is Laguerre function. Or Laguerre polynomial, whatever we call it. The differential equation is x into y double differentiation plus 1 minus x y differentiation plus n y is equal to 0, and n is equal to 0, 1, 2, 3, dot dot dot, and polynomial is represented in this fashion. We get lnx is equal to e to the power x dn by dx n x to the power n e to the power minus x, and it is also called Rodrick's formula, like in the case of Hermite. So anything that is based upon this quantity dn by dxn, it is you can call it as a Rodrick's formula. So you can see in the case of Hermite also the same type of expression came. This is so dn by dxn, so again some sort of Rodrick's formula. And the first few polynomials of Lagrange function are L L0x is equal to 1, L1x is equal to minus x plus 1, L2x is equal to x square minus 4x plus 2, and L3x is equal to minus x cube plus 9x square minus 18x plus 6, and lastly we have L4x is equal to x to the power 4 minus 16x cube plus 72 x to the power x square minus 96x plus 24, which is the last term, and the generating function is given as e to the power minus xs divided by 1 minus s divided by 1 minus s is equal to summation n is equal to 0 to infinity lnx to the power s to the power n divided by n factorial. The recurrence formulas of Lagrange polynomial, recurrence formulae are ln plus 1x minus 2n plus 1 minus x into ln x plus n square ln minus 1 x is equal to 0, and x ln dash x is equal to n ln n x minus n square ln minus 1x. So these two are the recurrence relation of Lagrange polynomial, and the orthonormal properties. Orthonormal properties are 0 to infinity e to the power minus x, L to the power mx, ln x, ln x dx is equal to 0 if when m is not equal to n, and 0 to infinity L e to the power minus x ln x to the whole square dx is equal to n factorial whole square. So it's quite interesting, this one, n factorial whole square. So this was all about Laguerre polynomial. The next polynomial that we will discuss in the next function is called the Bessel function. And it is given as j in x, and the differential equation corresponding to it is x square while double differentiation plus x y dash plus x square minus n square y is equal to 0, where n is greater than or equal to 0, and the expansion formula a generating function, whatever you may call it, or in the case of Bessel is j n x is equal to, or k is equal to 0 to infinity minus 1 to the power k x by 2 into to the power 2k minus n squared complicated divided by k factorial into gamma k plus 1 minus n. So coming to the properties of Bessel functions. First property is j minus n to the power x is equal to minus 1 to the power n into j n x, where n is from 0 to 1 to. Second property is this is minus 1. The property is j 0 dash x is equal to minus j1 x, and the last property is jn plus 1 x is equal to 2n by x jn x minus jn minus 1x. So this is actually not the generating function, this is the expression of Bessel's. Now the generating function of Bessel is e to the power x to the power s minus 1 by s by 2 is equal to summation n is equal to minus infinity to infinity jn x to the t to the power n. This is generating function of Bessel. So this was all about the different types of polynomials.